In this part of the lecture we will take a look at Ito-Taylor series of SDEs. We will start with Taylor series of deterministic ODEs to get a feeling of the ideas first, and then we will proceed to Ito-Taylor series of SDEs. Taylor series expansions in time direction are classical methods for approximating solutions of deterministic ordinary differential equations. In practical use, they are largely replaced by Runge-Kutta type of derivative-free methods, but whose theory is actually based on the Taylor series. Ito-Taylor series can be used for approximating solutions of SDEs in the same way as Taylor series can be used for approximating solutions of ODEs. The stochastic Runge-Kutta methods are also based on Ito-Taylor series, but they are not as easy to use as their deterministic counterparts. However, it's much easier to understand Ito-Taylor series by understanding the ordinary Taylor series first. This basis will also help to understand stochastic Runge-Kutta methods during the next lecture. Let's now consider the following ordinary differential equation, which is the time derivative of x is given as f of x and t, and we assume that x at t0 is given. If we now integrate both the sides and move x t0 to the right hand side, we get that x at t is equal to x at t0 plus the integral from t0 to t of f x tau tau d tau. Now we can use the trick that if function f is differentiable, we can also consider f x t as only a function of t and write the differential equation for it. So the differential equation reads the time derivative of f is equal to the partial derivative of f with respect to t plus the sum over I of the derivatives of xi with respect to time times the partial derivative of f with respect to xi, which in turn is equal to the partial derivative of f with respect to time plus fi times the partial derivative of f with respect to xi's summed over I. So we have just replaced the derivatives of xi with respect to time with fi by the definition of our ODE. If you now integrate both sides of this equation, we get the following. So f at xt t is equal to f x t0 t0 plus the integral from t0 to t of the partial derivative of f with respect to time plus the summation of fi's times the partial derivatives of f with respect to xi's. We can now simplify the notation by defining an operator like this, which is going to replace the two derivative operations on the right hand side of the equation. With this notation we can write the integral equation in this notation. So f at xt t is equal to f at xt0 t0 plus the integral from t0 to t of the linear operator L applied to f x tau tau d tau. Let's now recall that the integral form of our original ODE was xt was equal to xt0 plus the integral from t0 to t of f x tau tau d tau. But now if we use the result from the previous slide, this can be written as x t0 plus the integral from t0 to t of f x t0 t0 plus the integral from t0 to tau of the linear operator applied to f x tau tau d tau. And notice that the second integral is inside the integration. So this is actually equal to x t0 plus f x t0 t0 times t minus t0. This is because the first term above doesn't involve tau at all, and we can integrate over t explicitly, which just brings in the term t minus t0. From the second term we get double integral, where the first is from t0 to t and second is from t0 to tau, and the integrand is the linear operator L applied to f x tau tau. And again we can use the same trick to the integrand on the right hand side. So we can write down the L times f, or L applied to f, as the solution to a differential equation, which in this case is given as the time derivative of the term is given as the partial derivative of the term plus fi's times the partial derivatives with respect to x. But this is now exactly equal to the linear operator L applied twice to f. So we can now see the benefit of our notation that we introduced. So again, in integral form, this differential equation is L applied to f xt t is equal to L applied to f xt0 t0 plus the integral from t0 to t L applied 2 times to f of x tau tau d tau. We can now substitute this into the previous equation, which now gives this kind of expression. So we have now expressed the integrand, which was L applied to f, as contained in the term above. If we now open it up, we will get that xt is equal to xt0 plus f xt0 t0 times t minus t0, which we already had before, but now the new term is half times L applied to f xt0 t0 times t minus t0 power to 2, plus then a triple integral, where the integral is L power to 2, meaning L applied 2 times to f x tau tau. If we now continue expanding the terms with rules like this, we get the following Taylor series expansion for the solution of the ODE. So xt is equal to xt0 plus f evaluated at xt0 t0 times t minus t0 plus half times, which is equal to 1 over 2 factorial times the L applied to f xt0 t0 times t minus t0 power to 2 plus 1 over 6, which will be actually equal to 1 over 3's factorial L applied 2 times to f xt0 t0 times t minus t0 power 3, and so on, where this L operator is defined to be the time derivative plus multiplying with fi and taking the partial derivatives with respect to x's. We can now recover the Taylor series for a given function xt by setting ft being equal to the time derivative of x in the above equation. So if we do that, we will notice that we will have the time derivatives of x instead of f there, which is the ordinary Taylor series. Let's now do the same kind of derivation of the Taylor series for the SDE of this form, which is given as dx is equal to f xt t dt plus L xt t times d beta, where beta is again a Brownian motion. In integral form, this is xt is equal to xt0 plus the integral from t0 to t of f x tau tau d tau plus the integral from t0 to t of L x tau tau d beta. Previously, we wrote down f as a solution to certain differential equation, and we used the chain rule on the right hand side. So what we will now do instead is that we use the Ito rule for f. So the Ito rule gives that the df is equal to the partial derivative of f with respect to times dt plus the sum of partial derivatives of f with respect to x's times fu dt plus the sum over u's of partial derivatives of f with respect to xu times L d betas plus half times the second partial derivatives of f with respect to xu xv times lq L transpose then times dt. Here we have already substituted dx's to the Ito formula. However, in this case it's not enough to only expand f, because we also have another integral which contains L. But for the L we can use the same thing, so we use the Ito formula to expand it, which gives dl is equal to the time partial derivative of L dt plus the xu partial derivatives times fu's dt plus then the x partial derivatives times L d beta plus then half times the second partial derivatives times lq L transpose dt. Now we can integrate both f and L, which give expressions like this. So f is equal to f evaluated at t0 plus the integral of the partial derivative with respect to time, plus the integral of partial derivatives with respect to xu's times fu's, plus the integral of partial derivatives with respect to xu's times L d betas. So these are stochastic integrals, plus then the integrals of half times the second partial derivatives times LQ L transpose d tau. So these are ordinary integrals. For the L, we have similar terms. The first is evaluation at t0, then the integral of the partial derivative, which is ordinary integral, plus then the integrals of partial derivatives with respect to xu's times fu's, and then the stochastic integral of the partial derivatives of with respect to xu's times L d beta, plus then half times the second partial derivatives. Now again, as in the case of ODEs, we can try to figure out what kind of operators should be defined so that these can be written in shorter form. So what we end up is that it's useful to define these operators. So we have LT of g is equal to the time derivative plus the partial derivatives with respect to xu's times fu's, plus half times the second partial derivatives with respect to xu xv times LQ L transpose. So this is the same as our original L, but we have the second order term there as well. It's also useful to define another operator, L beta v, which is the partial derivatives with respect to xu's times LUV, summed over u. Then we can conveniently write both f and L as follows. So f is equal to f x t0 t0 plus the integral of LT applied to f d tau, plus then the stochastic integrals of L beta v applied to f over d betas. And for L, we have analogous expression. Finally, we can substitute these into the equation of xt, which gives expression like this. So x is equal to xt0 plus f xt0 t0 times t minus t0. This was also appearing in that deterministic case, but then we have L evaluated at xt0 t0 times beta t minus beta t0. So this wasn't in our ODE expansion at all. But then we have integral terms, where the first one is double integral of LT applied to f, and the next one is the stochastic integral of L beta v applied to f. It's a stochastic integral over b and integral over tau. The next term is double integral of LT L, first with respect to tau and then with respect to beta. And finally, we have a double stochastic integral of L beta v of L x tau tau with respect to d beta v and d beta vector in our notation. This equation now can be seen to have this form. So xt is equal to xt0 plus f xt0 t0 times t minus t0 plus L xt0 t0 times beta t minus beta t0 plus r, where this r is a remainder term, which contains all the integrals here. And if we actually ignore this remainder term rt, this gives the Euler-Maruyama method. The error is given by the integral terms left on the right hand side. And this is actually the way that we can use to derive higher order approximations to the SDE. So we can expand more terms on the right hand side in the same way as we did for ODEs to get higher order methods. Of course, details become messy, but it's straightforward in principle to do.